Let's talk about the time and space complexity of the algorithm for multiplicative persistence. If you aren't familiar with the problem, here it is. Given a non-negative integer, write a function that returns its multiplicative persistence, the number of times you must multiply the digits in a number together until you reach a single-digit product. I believe the difficulty level for this problem is easy. The solution can be done either iteratively or recursively. However, iteration is more optimal due to the fact that recursion pollutes the call stack. So for example, given a number 39 here, it takes a total of 3 steps to get to a single digit 4. And we return the total of steps. The solution is fairly simple and straightforward. I use the recursion and reducer for my solution and store the steps in a variable count as an additional argument. We convert the number to the string to get its length. If the length is 1, that means we have a single digit. We return count. Every time we run the function, we increment count by 1. Using reducer to get the product number and then recursively call the product number until it reaches the length of 1. So here's the reducer method, and this is the recursion. And we finally return count. So if we run the function on 39, we get 3. And if we run the function on the number 1, we get 0. And to run the function on 111, we get 1, which is the answer. So everything worked. But when I asked myself, what is the time complexity of this algorithm, I was completely stuck. The time complexity may first seem like O of n because of the reducer method, which is O of n, or O of log n, because every time we multiply the number, it cuts the time for the next multiplication down by half, approximately. But let's compare some numbers. Number 111 takes 1 step to get to a single digit. What about this large number here, 9 with 18 zeros behind it? It also takes 1 step. The input size increased drastically, but the step to take it to reach to a single digit is the same. And number 39, which is smaller than both of the previously mentioned numbers, takes 3 steps. This number here takes 11 steps. Number 544, which is between 39 and 111, takes 2 steps. What do we see here? We don't see a pattern. It's almost like it's random. With the help of peers Natalie and Aleks, we concluded that the time complexity of this algorithm is actually uncalculable because the time it takes to get down to a single digit in relation to the input size is inconsistent. It will largely depend on the digits of the number. In regards of auxiliary space, iteration is O of 1 because we aren't taking any more space when we iterate through the number. But auxiliary space for recursion is also unknown because, again, it depends on the digits of the number. I want to give a special shout out to Natalie and Aleks, both of whom are extremely intelligent and helped me with the big O notation of this problem. Aleks recently started a YouTube channel on algorithms and data structures. Please check it out. And please take a look at their LinkedIn profiles. I have included all the links with this video. Thank you again. Bye.